Okay, so what we did last time, we discussed that we have two related quantities. Which are continuous. By continuous, I just mean that the quantities takes values in real numbers. So this is when you have such a situation, again, informally speaking, we have a function of a real variable, function of a real variable, taking values in real numbers. So one quantity over here, you have two quantities. One quantity is which you give as an input, and there's another quantity, both are real, which is an output. So you have this kind of a machine. This is the function. You give it a number, and it outputs some other number. So takes in real numbers and relates it to some real number. Now, the calculus is just the study of these functions. Whenever you are studying functions, these relation between continuous quantities, quantities which takes value in real numbers, or more general numbers which are of continuous type, like complex numbers, relation between them using these functions, that study is calculus. In this course is the simplest one, where you are just relating one real variable with another real variable. So functions of only one variable. So all information about the function is known if we know the outputs for all the inputs. Well, that's all there is to the function. That's what it does. It takes in values and gives you output. So if you knew all the list, if you knew the full formula for the function, you have in principle all the information about the function. So let me write over here all information about the function. And what's the function? It's just relation between these two quantities is known if you know all outputs for all inputs. But if the information is there, that doesn't really mean that you really that it's in some useful form. So even if you know the function completely, you may want to extract some useful quantity, some useful information out of it. So a very useful information that can be extracted from the data of function. By the data, I mean input and output relations. A very useful information is the rate of change of quantity 2 as you change the quantity 1. In other words, rate of change of y as x changes. How quickly y changes if you change the input. That's a central piece of information which you can extract as x changes, and this you want to compute at a particular value of x. And then you want to know it for all values of x. So then you will have an extra information coming up about this function and its behavior. So this bit is central, and it is the derivative of the function. This information in principle is buried in your data of the function, but something being available and something known to you is a different matter. So you need techniques to extract this information from the data. And those techniques are the techniques of the differential calculus. This part of calculus where you compute the rates of change, this is called the differential calculus. Now, moving on with some more discussion of it. We took the metaphor of motion last time. Let me consider another example today, and this is the metaphor of the hill. By the way, is there a question about what I just said so far?
Sir, what is meant by metaphor of the hill?
Yeah, that's what I'm gonna discuss now. So one variable functions, you can understand them through this metaphor. If you want to make sense of them and make a mental model, you can think either in terms of motion, as we discussed last time, or in terms of climbing a hill. And how do you do it? I'm just going to discuss it. Zishan has a question.
Yes, sir. My question is that, sir, I didn't get the point that what function is exactly itself, sir.
Well, for now, we are just discussing it colloquially in simple, plain language. So what it really is that you have a set of numbers, you have a variable which takes values in real, and function relates it to some other numbers. So for example, as we discussed last time, for each position, if a car is moving, for each time, you have a particular position. And similarly, for example, we can consider this metaphor of the hill. So what do you have over here? So suppose you have a hill. And you're climbing it, maybe on a bike. Now, to describe this hill, you have, for example, how far away you are from particular mark post. For example, this is the city center, town center, and this is the horizontal direction. But you're not going straight because you're climbing up a hill. So you can ask how up I have gone. So those readings you can mark over here. So this is the horizontal and this is the vertical direction. And if you are at any point on this hill, you can, for example, read off how far away you are from your initial point or any standard point. Let's say, call it x2. There's a corresponding height you have. let's say it's y2. So what you are doing over here, at each horizontal position, you have a particular height up the horizontal because you're climbing up the hill. So this hill is relating with the horizontal direction a height. So this is a function for you. So the two related quantities over here are the height and distance, horizontal distance. Let's say from town center, and height above the height from the sea level of the town center, for example, any standard point. Now, so you have this, then you can talk about, you can have this hill, or you could have another hill. So the difference between this hill and this hill, the black and the green hill, is that the green one is much steeper compared to the black. Similarly, I can think of some other hill which is even less steep. So this steepness of the hill is actually, what is it? It's how high you climb up as you move a particular horizontal distance. How quickly the hill is rising up. So this you call, in common language, the slope of the hill. Steepness of the hill. And what is this? This is nothing except the rate of change of y as x changes. Now you can think of it as a graph. This is the x-axis because I called the horizontal distance x. And this is the y-axis because I called the height above the sea level as y. You can think of it as a graphical representation of a function. It's a very special kind of function, very simple function because it's just a line, but still it's a function. It's relating variable x to variable y. And that quantity which I said we will always be interested in, rate of change of y as x changes, in this case has a very easy interpretation. It's just the slope of this hill. It's telling us how steeply the hill is climbing. Now, how can you calculate this slope? How can you give it a quantitative measure? First of all, notice that if you were on this point over here, there's no way for you to tell if you were climbing the hill, the green hill or the black hill. And if you are just at this point, which I just marked over here at distance x2, for you, there's no way to tell how steep the hill is standing at this point, because regardless of if you are on hill, black hill or on the green hill, your distance from the town center is x2 and your height is y2. Both hills at this point have same distance and same height. So standing at a point, there's no way to tell on which hill you are, which is related to the fact that standing on a point, there's literally no way for you to tell how quickly the hill is rising. So you can't tell the slope or the steepness standing at a point. You have to cover some distance to see how quickly the hill rises. So that's why to define the slope, you need a certain horizontal distance. You have to cover a certain horizontal distance. If you knew about this whole length of this hill, let's call it delta x, and this whole length of height of the hill, delta y, then you can make this ratio and call it the slope. But suppose that this hill, which that's how I drew it, the hill is very smooth, or in other words, the hill is just a straight line. If the hill is a straight line, then it means that it's a very special kind of relationship between x and y, between horizontal distance and the vertical height. So that special relation between x and y, if it's a straight line, is, if you recall, is given by this kind of relation, where this number c is very easy to interpret. So what do I mean by that? This is given by this equation. It means every point on this hill, no matter where you are, satisfies this equation. Every point on the hill satisfies this. So in other words, we mark that point y2, x2 and y2. So this would be true for that point. And if I look at another point over here, let's say this is x1 and correspondingly a value y1. So same equation will hold for y1, x2. Alpha and c are some constants over here. They will not change. These are variables, y and x are variable. And
Sorry to interrupt, sir.
wait, you can pick any point on the hill, put its coordinates here, and it will be satisfied for fixed values of alpha and c. Yes, Ibn Masood, your question?
Yes, sir. Assalamu alaikum. How do you derive this?
Oh, well, right now I'm not deriving it. I'm just recalling it, and just take it as a fact. If you don't recall it from high school,
Okay.
just take it as a fact. That if
Okay.
it's a straight line, then all the points on this are described by this equation. Now, so the C then is very easy to interpret. What is the C? If I put x is equal to 0 over here, so I come over here, it has a certain value for y. For this hill which I drew, the value for y is 0, but it could be something else. For example, it could be I could put the 0, the city center over here. Let me change this hill a little bit. Let me remove this. I'm not changing the hill. I'm just changing the position of the city center. In other words, changing the origin. So when you are at the city center, you are not at the sea level. You're already climbing up the hill. So you have a particular value for x is equal to 0 for the height, and that will give you y is equal to c. So this c is just intercept of the hill with y-axis at origin when x is 0. So in other words, how high is the city center at over here? So that's easy, but this one we don't know yet. On the other hand, as I said, that I can find the slope or steepness of the hill by computing the whole distance, the height of the hill over here, and how long is this hill. But notice that if this hill just keeps continuing, I wouldn't want to do it. I would take 2 points, like this x2 and x1, and I'll just compute that when I cover this distance, how much I climb. And this gives me the rate of climbing, rate of increase. So I can say that the slope is the change in the height divided by how much horizontal distance I covered between those 2 points. Now, if you, instead of this, choosing this point, if you say, what if I compute it using a third point? This is not y3, this is y3. So someone, they don't cover this whole distance from x1 to x2, they just cover from x1 to x3, and then they try to figure out how quickly the hill is climbing. So what would they do? They would use y3 minus y1 over x3 minus x1, that how much high they climbed when they covered a certain distance. For this line kind of hill, for this straight line, the property is that if I compute this number, y3 minus y1 will give me because c will cancel when I'll put these values. So it gives me alpha, slope alpha. And over here also, because all these points satisfy this equation, I'll get alpha. So you can compute the slope using any 2 points. You always get the same answer, which is intuitive because this hill is rising, as you can see from this picture, at the same rate. Doesn't matter if you compute it here or anywhere, or how many points which points you include. It's rising at a steady rate, which turns out to mean that you can choose any 2 points to compute the slope. And it always gives you alpha. So this number in this equation is just the slope of the line of the hill. So that's some simplification. But this also tells you that this was just an algebraic operation. What if I want to know? First, I said that you cannot compute the slope. You cannot tell how quickly it's moving. It's rising up, standing at a point. But this gives me an idea that the slope can be computed using any 2 points, which we already, any 2 points, doesn't matter, you always get the same answer. So then you conclude no matter how close the points are. So you can, for example, compute the slope by doing this y2 minus y1 over x2 minus x1. And then you then take that x2 is extremely close to x1. I haven't defined it properly, this symbol, but I'm using it in the same sense as I used last time, that bring them very close. So last time I said that it should be well defined. In this simple case, this looks pretty well defined, because as long as I am not putting it exactly equal to x1, I don't have to say how close I am. I can go as close as I want. That doesn't matter, because as long as they are not same, these will always cancel, no matter how close they are. And you don't have to say how close they are. You always get the same answer. So this kind of situation, you're going to say that the limit exists, and you can define, let me put define in inverted commas, the slope at one point. Because kind of you're doing the operations in very, very nearby regions. So we can just call it, that's the slope at point x1. But still, it's not very interesting, because it is certainly a good definition of slope at one point, but it's the same slope all along the hill. So who cares if it's at point A or point B or point C? So let's consider a bit more general slope. So suppose the hill looks like this. It's like this, but then it becomes steeper. And over here, this is x, this is y. Over here, I'm going to plot the slope of this hill as you change x. So it's quite intuitive that what we should be doing is that the steepness of this hill is different in this region and is different in this region. Because this is one line, this is line 1, and this is line 2. Mathematically, these lines do not have the same equation. They have different equations, so they have different slopes. And also pictorially, intuitively, you can see they have different slopes. So I should get different answers. So if I want to find the slope of this part of the hill, I can choose any 2 points over here. Maybe these ones or any small ones, doesn't matter. But some points in this region. And if I want to compute the slope over here, then I should choose some points in this region. If I choose a point here, this, let me use some other color. This point B and this point A, I will not be able to define the slope using my previous formula, because I don't have an equation of line. These are two different lines. And I can't assign one single slope, maybe something average, but not what I was doing before. So clearly, this hill, if you want to describe its steepness, you are describing slope as a function of x. As you change your distance from the city center, first you encounter a certain rate of rise, and then it changes. So you can say, I can plot it. First I had a constant slope, and then the slope changed. It became more. Something funny happens here, so let's not trust this part. But as long as I stay away from this kink, this is pretty much the graph of the slope. So what we have learned is that the slope for a hill, and hill for us will become a general metaphor for any function of one variable. It can change from point to point. because hill steepness can change from point to point. And the derivative is essentially an operation which takes the graph of the function. So this is the graph of the function over here, and converts it into the graph of the slope of the function, or more appropriately of the derivative of the function. Let's call it differentiation. So that this is an operation and this is the derivative of function, and this is the function. Now, if I consider a more general, by the way, if I draw this same graph for this previous hill, graph of the derivative or graph of the slope, it will be just a constant line because this slope does not change as I move in the horizontal direction. Now, generalizing this idea even more, I can consider a more general hill. So how would that look like? So that hill could be like that. Make it a bit smoother. Now, what you want to do, you want to describe, certainly it's a hill, and at some points you will encounter, you will have to do harder work because it will be like over here, it will be very steep, while you will have some respite at this point because you can see that it's not that steep. So the rate of change of height is changing from point to point. At some points, this hill is steep, at some points, not that much. So you want to assign a slope at every point. So the idea is that how you're going to do. So like just like over here, you choose a region where you want to define it. And if you want to define it for a point, the idea is that for two very closely chosen points, this hill still looks like a straight line. If I zoom it, I'll may discover some new features, but from here, it looks like a straight line. So I can, for a small enough point, the hill looks like a straight line, and we can define slope. So over here, define the slope by our previous formula, which is that I take these two nearby points, compute their y values, and their x values. So since for a small enough region, any hill, if you're standing on a hill, even if it's like wavy, at that point of the road, it looks straight, almost straight. So you approximate it as a line, and then you can use your formula for the line, for the close enough points, for the steepness of the slope at this point. Slope at point x1. Talking in terms of line, this alpha is the slope of the secant line. So what you are doing, you are choosing some close enough points, and if you're given any 2 points in the plane, you can draw a line through them. If I have these 2 points, I can draw a line through them. So since you chose 2 nearby points, you can draw a line through them. And when you draw the line, since these points are nearby, you expect this line in this region between these 2 points to coincide with the hill. That's the idea. That between these 2 points, this line which you have drawn as a line connecting these 2 points approximates the hill. So this line is called a secant line. What is a secant line? Line drawn to 2 points on the graph of function. And for us, to 2 points on the hill. I could have chosen these faraway points. Let's say this one and this one. And this would be the secant line. But this secant line will not approximate the function. It will not coincide with the function between these 2 points. Function goes some other way, and the secant line is marking some other points. Only when these points are very, very close, then the secant line approximates the function. Also, when these points are very, very close, then you call the secant line, you give it a name. When the 2 points are very close, very close, this is called a tangent line. To just define a tangent line, you need the idea of a derivative, but intuitively, it's just the line which is grazing the graph at that point. And it's like touching it at one point, and it's going in the same direction where the graph is going. Like this line, this red line is going in the same direction, or is coinciding over here with the graph and touching it at one point when you bring these 2 points very close. So you take the slope of this line. So slope of the tangent line gives you the idea of how steep the hill is. In other words, the slope of this tangent line is computing for you the rate of change at this point, which is the same thing as computing the derivative at this point. However, let me raise a complication. If we don't know, well, let me first take some questions. Is there a question? Anyone wants to raise their hand?
Sir, can I speak?
Yeah.
So the tangent line and the secant line are kind of similar.
Yeah, secant line becomes a tangent line when the 2 points become very close. Shahi, it was Shahi. Okay. Is there another question?
Sir, can you explain this point again?
Yes, sir.
Explain which part again?
जो शहीद का आपने अभी बताया, like.
Well, that's, I mean, you can go back. I'll upload this and read it again. Essentially, all I'm saying is that the function is changing from point to point. It doesn't look like a line at any of this. Throughout this hill doesn't look like a line, but I want to give it, I want to talk about the rate of change. So what do? I just focus on some very nearby point, and I ask how high the hill is climbing around in this region. So how would you do that? Obviously, you would look for nearby points and then try to compute the rate of change. All I'm saying that you can do by drawing a line through those 2 nearby points. That line will approximate this hill between those 2 points, and that line's rate of increase would be the same as the rate of increase of the function between these 2 points. So rate of increase, you always need 2 points. But since you want to be mathematically very precise and want to say that this is the rate of increase at one point, so all you do is bring those 2 points very close. And when you bring those 2 points very close, this secant line becomes, you just give it a name, you call it a tangent line. So Saira, you have a question.
Sir, in the above graph where you have drawn two lines which have different slopes, so can we find their slopes by differentiating their equations?
Well, we haven't really talked about differentiation properly right now, but you can definitely do it, because if you know the differentiation from your high school, you would know that when I differentiate this equation, this is the equation of a line, dy by dx is just alpha. And that's what we found by algebraic methods, that the slope is alpha. And differentiation also gives you alpha. So it's the same thing. Ali Hussain.
Sir, मुझे ये समझ आ गया कि the tangent is gradient at a specific point, लेकिन I still don't understand secant line क्या थी, because your
Secant
voice
line
lagged when-
is any line written over here, line drawn through 2 points on the graph of function. So if I take these 2 points, this blue line would be secant. If I take these 2 points, this line would be secant. When the points become very close, then the secant becomes the tangent.
Got it. Thank you, sir.
Abdul Rahman.
Sir, can we join the two gradients in the second graph above?
This one? This one?
Yes.
This one? No, you mean these two?
The second one.
Over here?
Yes.
No, we can't. So something strange happens at this point, because you can't, you have one line and you have the second line. So at this point, which slope you want to give? You're confused. So we haven't resolved that issue yet. Shahid.
Yes, sir. I just wanted to know that, as you mentioned, that when 2 points get very close, it's called a tangent line. So are we implying?
Can you speak up? I can barely hear you.
Sir, am I audible now?
Wait, let me increase my volume. Yeah, speak now.
I'm audible now?
Yeah.
So, sir, as you mentioned that when 2 points get really, really close, it's called a tangent line. So are we implying or assuming here that the 2 points are so close that we take them as one single big point, because tangent can only pass through a single point, right?
No, that's not the actually the definition of tangent. We will discuss the definition of tangent much more carefully later on, but that's not how we're going to define the tangent. Tangent is a secant line when the 2 points come very close. Colloquially speaking, you can say, well, since these 2 points are very, very close, so it's as if this line is touching it at one point. Because let me give you an example. If I take your definition of a tangent, what is the tangent over here at this point? You would say it's this. It doesn't touch this graph at one point, it touches it at 2. But still you call it tangent. Why you call it tangent? Because you took 2 points over here, let's say this one, and you drew a secant line. And secant line doesn't say how many times it has to touch. It just says that you pick 2 points on the graph and draw a line. So I drew this line, and when I brought them closer, the secant line started to rise up. And when they were very close, this became the secant, and you called it the tangent. All right, so let me move on. And if you still have questions, I'll be available after the class, so you can ask me. So let me just move on. Now there's an issue over here. I said, so what I'm saying over here, I am saying that if you look close enough, then this hill looks like a straight line, and you can approximate it by that straight line and call the slope of that straight line as the slope of your hill. But there could be an issue. What's the issue? So let me draw over here that this is the slope. You look over here and you find this kind of, this is the hill, you find this, and you choose 2 nearby points, and you expect that this is the line whose slope you have to find. But now you zoom in You have a big magnifying glass and you zoom in. When you zoom in, you find out that between these 2 points, actually the function was wiggly. The slope was wiggly. From far away, it looked like a fairly smooth road, but they were like speed breakers over here or some bumps on the road. So now you are again confused because which line you should take? Those were the 2 points and you had drawn this line. But now if you come closer to this point, you can take this tangent or this one, sorry. You can take this tangent or this one or this one or this one. Which one you should take? So that means if you don't have the full information about the function, you could be mistaken. So if you truly want the slope at one point around over here, you have to go down to the resolution that this secant line, this tangent line no longer wobbles. Over here, as you guess that this is your tangent line, but when you zoomed in, you found that this is probably not the right guess. There are other guesses available. So if you can go to a resolution so that when you go even further finer in your resolution, the tangent line stabilizes. For example, you discovered that this looks like this. Now you zoom in over here. Now when you zoom, you find that it stays the same. And the tangent you have draw stays the same as this one. They're the same tangent. So then you say, now I'm truly finding the true tangent over here or the true rate of change at this particular point. And then you say that your limit exists. So limit is the slope when tangent line no longer wobbles, when you increase the resolution. So limit is the slope when tangent line no longer wobbles or changes when you increase the resolution. In other words, those 2 points you chose to draw the secant, when you bring them closer, they converge to start giving you one particular line. And no matter how closer you bring them, that line doesn't change. If that happens, then you have a proper tangent defined at that point, and then you have a proper derivative defined at that point because the limit exists. But this can very easily go wrong. I can give you some examples where this may not happen. So it's quite conceivable that no one tangent line is defined. So how can it happen? For example, as you had increased your resolution, you discovered that it looks like this. You zoom in further, this one again looks like further. So as you keep zooming in, it keeps wobbling. It's a very ugly kind of function. So then you won't have a tangent. Keeps wobbling. Or you could have this kind of situation that at that point, the graph suddenly turns, the hill suddenly turns. Now you truly have this tangent and this tangent. Now you don't know at this point which tangent to choose. So you don't settle on one tangent. So again, the tangent doesn't exist at this point. And consequently, the rate of change of hill cannot be given a meaning at this particular point. Or it could be a sudden jump like this. So again, in the hill. So here the hill was changing at this rate. Well, let me draw it like this. Here the hill is changing at this rate. So you don't know how to give it a weight because you truly get two different tangents at that point. So it can happen that you don't get a limit. It's not a given that you will always have a derivative, and it's not a given that you will always have a tangent to the curve of a graph. Now, Saad, let me take a quick question from you.
And in case 2, what will be the mathematical output of it? Like if you say that the curve gradient is changing, so mathematically क्या होगा ये?
That means the derivative doesn't exist.
मतलब undefined आएगा?
Undefined, yeah. Well, you have to realize when you say mathematically is just giving precise words to the ideas we want to discuss. Okay, so when you say undefined, you have to know what do you mean by undefined. That's what we mean in this case, that we couldn't decide on which tangent to take.
Okay.
Let me move on.
Any point before this and after this एक specific gradient होगा, but at this point नहीं होगा.
Exactly.
Okay.
I just want to complete. Okay, let me take a question. Probably I'll again not complete today's lecture, and those things we can discuss later. So let me take one more question from Saad just asked. Faris, you have a question?
Sir, can we get summary of today's class?
I am not done with the class. Why are you asking for a summary? Muhammad Shayan.
Sir, time to know.
Time कहाँ से होने वाला है? We have 18 minutes left. Shayan, what's your question?
Sir, in the cases where you said no one tangent line is defined, the first one there where it keeps wobbling, is that the thing called Weierstrass function?
Yeah.
Okay.
Now, so in any case, what we have now is that we can, using this kind of limiting process, like looking at two very nearby points, we can talk about the rates of change, and or in other words, we can talk about the tangent lines. In other words, simpler words, the rate of change. So what the calculus does, or at least the differential calculus does, is, and you can always think of it in this metaphor of the hills, that you have this kind of a hill, for example, and think of it as a hill or as a function. You have correspondingly its rate of change or its slope. This is x, this is y, this is x, and this is the slope or the derivative. Well, all of you know, so I don't need to pretend that you don't know. The symbol for it is dy by dx. So given this graph, the task is to compute this graph. That how does the rate of change or the derivative looks like? So over here, if I try to just give a very rough kind of answer, in the beginning, the rate of change is large, and then it slows down and becomes 0. So it's something like, so this is how you are relating it with the derivative. There's always this goal. You're given the function, you want to compute its rate of change. And if I take the previous example, I had this. For this, it's very simple. It's just straight line. And if I take, for example, this hill, so what happened over here? It had in the beginning a certain rate when it was steadily climbing, so it was a constant rate, but then it suddenly had an increase in its rate. So the rate increased, but then it again decreased and became 0. So something like that. This is the function. This is the rate of change of function. And these could be any quantities. So this function could be any relating any two quantities, real quantities. And this will then give you some extra information. As I said in the beginning of the course, it gives you, it extracts some information from this relational relationship which is already given to you. It extracts some more useful information out of it. So for example, this could be a graph of price history. And this is the rate of change of price history, which is the inflation. At what rate the prices are increasing. So you will hear politicians try to confuse people. They say, like, for example, if the prices have stabilized over here, so that means the inflation has gone to 0. And one politician will claim we have reduced the inflation and it's about 0 right now. They will claim, well, when I was in power, the prices were much lower. So how are you claiming that the inflation has decreased? Well, because inflation is this graph, not this graph. You never see prices coming down. Well, you can see, and maybe I should draw that too. You could have a hill going down. What does that mean? That means you have a negative rate of change. As you cover a distance, y decreases. So the derivative, wait. So the derivative is negative. So over here, if the prices start to fall, this is what you call the deflation. And similarly, other examples could be, you have a, like from what we did yesterday, you have a position history of a car and you can give the speed history. You could have wealth and you have growth rate. So again, like GDP is different, GDP growth rate is different. No country usually goes down in their total GDP. So comparing GDP from the past with today is not a very useful idea. What one should be more concerned about is the rate of change, how quickly you are growing. So this graph, not this graph. Similarly, you can have, for example, in the hill example, height profile and slope profile, if these functions are literal hills. Yeah, so what's the question, Heather?
Sir, can you please scroll up to the df upon dy curve? Sure. Yeah, this one, the one you drew in green.
Yeah, this
down.
one.
Yeah, the second one.
This one.
In which you translated the second one. Yeah.
Yeah.
the straight line that you've drawn.
Yeah.
Shouldn't this touch the y-axis?
Yeah, it does.
Because the gradient at
Yeah.
okay.
Sir, the one above that. The one above that.
Yeah.
Shouldn't it have constant gradient at the starting? So won't it be a flat line at the start and then it depreciates?
Well, I'm not being very accurate. As I said, that I'm just drawing freehand, and I don't know. I'm not drawing actual depictions. I don't know if I want to draw a straight line. I just gave an idea.
Sir, can we use this as graph examples of displacement and velocity?
Yeah, exactly. This could be displacement, and then this would be velocity. So let me move on. We can, so as I said, that this is what you do. Given this graph, you find this graph. This is called the differential calculus. But you can go the other way as well. If you're given this graph, you can go back and recover the actual. So if you know the rate of change at each point, so in other words, if you know the speed of car at each moment of time, you can compute how much distance it must have covered in a certain amount of time. That kind of problem, going from this graph back to this one, that is called the integral calculus. So that's one part of the problem. So essentially the calculus is relating these two things in either direction. And it's kind of very obvious that how would you do it? So for example, if I consider this, you have time here, you have distance. You have a car moving at constant speed. So that would be a line. And constant speed means that if I draw this graph of the speed, which is the rate of change, then that would be a constant like this. Now, from elementary algebra and elementary logic, you know that the speed is just how much distance you have covered in how much time. And since it's a straight line, as we discussed, you can choose any 2 points, or you can do it at 1 point, it doesn't matter. But if we know speed, like over here, if we know this graph, if we didn't know this graph, if we know speed, we can find the distance covered. Knowing the speed, I already know that it must have come from a straight line. So I can compute this. And what is this? This is just, if I think in terms of hill, this is change in height which is slope times change in x coordinate. In this example, it is change in distance, which is speed, which is the derivative, times change in time. But what is this? This is a straight line and this is a straight line. If I multiply them, I get the area of the rectangle. So to get the change in height, all you have to do is, if it's a straight line, compute the area of the corresponding rectangle in the rate of change graph, like over here. But what if it's not a straight line? What if you are given this graph? This is the speed graph. And you want to discover the distance graph. So you're given this. and you want to translate back over here, the integral problem. Again, it's you're gonna do the logic this way. You know that if I consider two very close by points, I can probably approximate it as a straight thing. And for very close by points, if I consider a rectangle, this will give me how much distance has been covered, because that's what I had over here. Distance covered is equal to the area of rectangle. These are all just ideas. Don't worry that if you cannot note down everything or absorb everything. Obviously, it's just the area of the rectangle. So if I consider two very nearby times, it will be the area of this small strip rectangle. And then I can divide this whole thing into small strips.
Hello, sir.
Wait. Do not interrupt me. So I divide it into small strips. Each strip is a rectangle. You may object, well, it's not really a rectangle. It has some kind of non-rectangular side. I'm going to say that I'm going to bring them so close that this does not matter. Almost rectangle. And again, a limiting process will be involved. So what I do is adding up all the small strips. Gives me the total distance covered. Right? Because between any two times, a strip gives me the distance covered between that time. So if I add all the strips, I get the total distance covered. And I can start from here and add strips up to this point. So I'll know that up to this point, what is the distance covered? Then I go to the next point and compute what is the distance covered by adding the strips up to that point. So by connecting all these points, I will have recovered the original graph. So this problem can be solved by computing the areas of certain strips. But notice that I have to make strips really small and add them up. Trust the answer. If making them smaller doesn't change the answer. So that's the final step of taking the limit. Since you are incurring some errors over here, but you make them so small that these errors then finally do not play a role. Obviously, although you can think of certain functions where you cannot really do it. Even if you make them very small, you do not converge to a particular answer, then you would say that the limit doesn't exist. But if it does, then you can recover the other thing back. And you can notice that what you are doing is adding a large number of things. So it's a sum of a large number. of things, which you call sum of a series. And when the terms in this series become very, very large, this you say that when the number of terms in this series are very large, then, and even then the answer doesn't change, then you are arriving at a limit. This is looks like a different limit from what we were considering before, where we had some quantity becoming very small. Here we have some number becoming very, very large. Do not think of it as infinity, not some weird thing, infinity. This symbol has a particular meaning. It just means when you have very large number of things. So in differential calculus, you are concerned with these limits. In the integral calculus, you are concerned with the opposite limits. And in fact, you can just talk about the limits in their own right, even if you are not doing integrals. You can talk about limits of series, limits of sequences, and those are all part of the problem of calculus. So all of this we will be discussing from next lecture in much more rigorous and properly defined way.
So physically?
Wait. So today was like essentially we ended the overview of what kind of idea we will encounter in the course. Now I can take questions. And now you can also ask any questions you have about the course.
Sir, can I?
Wait. Let me call out. Kunuz bin Rashid.
Yes, sir.
Ji.
Sir, my question was that the strips actually they are not rectangular; they are actually trapezium.
Yeah, but that's what I said. That you make them so small.
Yes.
Yeah, that this becomes well. To be accurate, that these are trapeziums, but you make them so small that if you take this off, it doesn't really
Yes,
matter
sir.
much.
And sir,
You
my
can just
second
take,
question
yeah.
was that at any given point, if I draw a tangent on a curve, then will there be a secant line that has the same gradient as the tangent? Because the way you showed us is that we are bringing the secant line closer and closer to our designated point.
Yeah.
So the 2 points converge on one single point.
Yeah. Well, yeah, that's how you define the tangent. If a secant line converges when you bring the 2 points very close, if the secant line stabilizes, then that's the tangent.
Yes, sir. Okay, sir. Thank you.
So Abdul Rahman.
Sir, instead of limits, can you use integration if an equation is given?
Say again.
For the curve, we can use integration for more
Yeah, that's what
accurate
integration
area.
is. That's what integration is, what I told you. Shayan, your question.
Sir, I had a question about the book that you recommended in the last class. That will we be covering the whole book in this course?
No. We are covering I'm uploading the course outline today. We are covering, I guess, the first 5 chapters.
Okay, sir. Thank you.
So who else is there? I think no one. Okay. So I'm gonna
So did
stop
you
here.
upload the book on LMS? Did you upload the book on LMS?
Yeah, I will. I'll do all of that today. And I'll also upload these recordings.
Okay, sir.
The next week's physical, if allowed.
Physical abhi tak to yahi hai, and I'm pretty sure if I have to put a wager, I would say 99% chances that we will go physical.
Inshallah.
Okay, inshallah. Khuda Hafiz.